Okay, hello everybody. I think we are right on time, so we can get started. Firstly, welcome everybody to the 108th Night Talk. Today, our speaker is Huan Xin. He's a second-year PhD student at University of Rochester, advised by Jian Ka, and his research direction is reliable evaluation of large language models. Today, he will going to present his work accepted by EMLP 2025, which is on analyzing the uncertainty of large model as a judge. And I think this is also his first paper. His first paper got the SAC, the Senior Area Chair Highlights Award. So let's welcome Huan Xin, and you can get started whenever you're ready.
Okay, thanks, Haolen. And today I will introduce my work. This is my very first paper to get published. And the title is Analyzing Uncertainty of LLM as a Judge Interval Evaluations with Conform Prediction. Today I'm very happy with you as my audience to my presentation. This is also my first presentation online on live stream. Yeah. And thanks to the collaborators from University of Southern California and MBTU-AI, we finally won SAC Highlights Award in EMLP 2025. Then I'll introduce our work. Nowadays, we know that LLMs are very powerful. Yeah, it has deep multimodal understanding across different works, different tasks from different languages, image and videos. It can understand many results in different modalities. And it also has strong generalization across different tasks, say creative writing, translation, and coding. You can use it to polish your writing in sentence. Yeah, and thanks to RLHF and DPO, it has good alignment with human preferences, which means that LLMs know what is good and what is bad. Yeah, and beyond understanding, it can do good analysis and explanation. For example, you can say, okay, one contains good because blah, 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 blah. It has some reason to tell its evaluation. Yeah, this paradigm is called LLM as a judge. You can use it to evaluate everything. It uses LLM to evaluate a specific characteristic of any content. Typically, these content are model generated. For example, you can use the LLM to evaluate the faithfulness of a summarization or relevance or overall quality, and so on. You can also use the LLM to detect some safety problem of some contents. And there are three typical evaluation types in LLM as a judge. Say the first one is point-wise rating. You can use the LLM as a judge to give a single score. Say my score is 5, which means that this task or this evaluation might be perfect. And you can also use the LLM judge to do pairwise comparison to tell which one is better between A and B, two different results. And you can also use it to do list-wise ranking to give a rank to different contents or text results. Yeah. And here in our work, we focus on point-wise rating in LLM as a judge. The point-wise rating is to ask the judge model to rate a single score in Likert scale, typically from 1 to 5. Yeah, for example, like this. And it has better consistency to human judgments than static metrics, including Blow and Roach. And it also is more adaptive, scalable, and cost-effective than expert annotations. And it also faces some challenges in uncertainty and bias, because the rating would vary due to inherent randomness of the model. And even with same prompt, the ratings could be different. Imagine such a scenario that you and your best friend are doing the same task and you have finished the task, and you ask the LLM judge to evaluate the performance of your task, your work. But due to the inherent randomness or the uncertainty issue, your friend got better score than you, even though your results are exactly the same. So this kind of evaluation is unreliable. Then we want to make such point-wise evaluation more reliable by uncertainty quantification. Here we know that a single score evaluation is unreliable due to inherent randomness or uncertainty issue. And we want to know when is the rating judge confident or uncertain. And we think that one possible solution is we can transform the score evaluation into an interval evaluation like this. When the interval is very short, we might think that, yeah, maybe the judge model is very confident about its decision. If the score is inside an wide interval, maybe the judge model is uncertain of its judgment. Then comes the question that how can we have a reliable evaluation, say interval, that quantifies the uncertainty of the rating? And our answer is to use conformal prediction. This is a post-hoc uncertainty quantification method. Yeah, conformal prediction leverages conformity score to measure the reliability of the ratings. And it also use offline calibration to quantify the uncertainty at a certain level. It has the coverage guarantee that the probability of that the ground truth lies in the prediction set is higher than 1 minus alpha, where alpha is the user-decided miscoverage rate. And for our rating tags, the prediction set here is an interval. For example, given the miscoverage rate is 10% through the calibration process, where we use the calibrated uncertainty estimate, we can transform a single score for here to an interval here, where this this interval enjoys the coverage guarantee that the probability of the ground truth lies in the interval is higher than 90%, than 1 minus alpha here. Yeah. And then I will introduce some related work. Yeah, we have some methods to quantify the uncertainty or to know the confidence of the judge model. The most straightforward or effective method might be logic-based confidence. Say there is a consensus that token logics represent judgment confidence. In this paper, they also do the evaluations by LLM judge, and they extract the logics and compute the probability, and then it can use to compute the mean score or the mode score. In this paper, they also do the pairwise comparison. Yeah, and in this paper, they compute the evaluation confidence. This probability is extracted as the largest probability in the judgment distribution, the 7. For this, this confidence might be unreliable because you know that the models might be biased, and then the logic could be biased. For example, the judge model could be confidently wrong. So this confidence might be not reliable. Yeah, another type of confidence might be verbal confidence. This method is not currently used in LLM as a judge paradigm, but it is very easy to use because you can just edit the prompt and ask the judge model to tell you its confidence when it evaluates. Like this paper, it will ask the model to answer a question and finish. When the model finishes its answer, it will tell you its overall confidence. Yeah, similar to this paper, it will just give you a confidence score to know how confident it is about its answer. But this verbal confidence might be still unreliable because this confidence score is just another uncertainty score that needs uncertainty quantification. And then a simple yet intuitive method is that we can run the evaluation multiple times. Say a pioneer LLM as a judge work called geval. They evaluate 20 times for each task, and then they compute frequencies and take a weighted average here. But it seems that the result didn't become better. Yeah, and Another paper, say this one, it used even more complex design to get the uncertainty level. Say you will first do bias assessment, that it will persuade an LLM judge to believe that a wrong choice, a wrong rating is right, and ask it to argue. And then it extracts the belief by the mean token probability of these assessments to construct a confusion matrix. And on this confusion matrix, it knows the uncertainty level. Though I think they are not still not very reliable. And the most important problem is that for each evaluation task, they need 25 runs. Yeah, which is very complex and computational heavy. The most related work to our paper is this one, which also use conformal prediction, but they focus on pairwise comparison to guarantee human agreement. Yeah, to sum up, I think that the reasons that we use conformal predictions instead of other methods is that prior works have some limitations. The first one is overconfidence, that the judgment model could be confidently wrong, which makes logic-based confidence and verbal confidence unreliable. And the second limitation is about the multi-runs methods. It uses multiple runs, so the LLM as a judge paradigm is no longer scalable because it is computationally expensive, while the results might still be unreliable. Yeah, because the most important limitation is that these methods have no statistical guarantee, while conformal prediction has this. In a preliminary experiment, we found that the ratings of the LLM as a judge in point-wise rating has severe bias. Here we measure this bias by mean square error and mean absolute error, and you can see that the bias is very severe. Prior works also use conformal prediction in LLM research, but there are some differences between their works and our work. The first one is the evaluation type. Just now I introduced our most related work. That guarantees alignment with human in pairwise comparison, but we focus on uncertainty in point-wise rating to give a single score. And second difference is that the output is different. Some methods, they are designed for multiple choice question answering. They aim to generate non-ordinal label sets, say A and C, in multiple choice question answering problem. But we need an interval, say a continuous one, instead of an interrupted set like this. And the third difference is the goal. Some methods, say conformal language modeling, these papers aims to select responses with factority, which means they use conformal prediction to guarantee that the responses of the LLM has factority. But our work quantifies the uncertainty. We want to know the uncertainty of the rating instead of directly finding a more reliable rating. So to sum up our work, our goal is to quantify rating uncertainty of LLM as a judge in point-wise rating by prediction interval using conformal prediction. And by conformal prediction, we construct prediction interval with coverage guarantee. We measure judge uncertainty and bias by interval-wise. And thanks to conformal prediction, we only need a single run in test time after offline calibration. Then I will introduce our framework. Here, there are three key steps in our framework. The first one is about to rate an evaluation and output logics. And second one is offline calibration by conformal prediction. And the third step is that we use the results from the first step and second step to construct confidence intervals, which enjoys the coverage guarantee. Yeah, the first step is rating evaluation and logics extraction. The intuition is that the logics of the model response represents the confidence of each potential rating. The first step is that we can obtain evaluation of a task X by a specialized prompt P, say chain of thought prompt. And then the judge model will respond with its score, its explanations. And we can just simply target on the rating token Y0, the 4 here. And we extract the token logic of this target token. And these logics are used as features in following steps. Then we prepare calibration sets, zcal and ycal, and test feature ztest, which are used in following steps. For certain steps, we do the offline calibration by conform prediction. The intuition is that a specific quantile estimate covers 1 minus alpha % of the deviations. In this step, we will first compute nonconformity scores on calibration step, this one, and then we estimate a quantile Q hat over the scores here with miscoverage rate alpha. And it is estimated by this one, and this formula guarantees the coverage guarantee. Yeah, and the end here is the size of calibration set. For the third step, we predict the intervals towards more reliable evaluation. The intuition is that an interval can be predicted by the Q hat, the quantile estimate, to each test point. Specifically, for a test point z-test, we can construct an interval by this formula. You can see the nonconformity score here is smaller than the quantile estimate. And this formula enjoys this coverage guarantee, which means that the probability of the ground truth lies in the interval is around 1 minus alpha, where alpha is the user-defined coverage rate. Here is the example that we can have an interval for evaluation task, say this one, while the ground truth is 3 here. But a question comes that how to interpret non-integer endpoints, because in some scenarios, some endpoints like this might have no exact meanings. And our answer is very simple, that we can just run these boundaries to nearest ratings like this. And this technique is called boundary adjustment in our work. It is used to run a continuous interval to an ordinal discrete one. Actually, it is an adjustment to the nearest rating of the initial boundary. Say like this, we have an interval from 2 to 4. In our paper, we theoretically prove that this adjustment technique has non-decreasing coverage. We will later show its experiment results. And here we comes the experiment part. We do extensive experiments on different settings across different tasks, say summarization and reasoning, and we also test two judge framework, including G-eval and Soccer eval. We also test different judge models, including reasoning models and non-reasoning models. We use 9 conformal prediction predictors to predict the intervals, 7 for continuous interval predictors, and 2 for ordinal discrete interval predictors. And for each experiment, we run 30 times to check the robustness of our evaluation framework. This one is our main results. You can see there are many results. For summarization tasks, we found that conformal predictors consistently achieve 90% coverage rate we want. But for reasoning tasks, some coverage rates are below expectation, perhaps due to small size in calibration. We will explain this later. And in our appendix, we have more additional results to support similar findings. Then is the result of boundary adjustment. The problem is that we found that coverage rate sometimes to be significantly lower than 90%. Say like this one, you can see the coverage rate is around 83%. But with boundary adjustment, we can increase this coverage rate to around 88%. And we found this increasement exists on all experiments, which means that all coverage rate improve while the interval remains. on all experiments. By the way, we test different conformal predictors, and we found the best predictor is R2CP, which achieves best trade-off of coverage rate and interval-wise. And here we want to explain why the boundary adjustment is effective. We found it can increase the coverage when the boundary adjustment will expand the boundary to the ground truth if it is the nearest rating. Here you can see an example that without boundary adjustment, you can see the ground truth is just outside the interval. But if we can expand the interval boundary to its nearest rating, the 5 here, then these ground truths are included in the interval. Well, you can see the coverage rate has increased from 86% to 90%, and the average interval-wise remains. Then another problem comes that what can I do if I still want continuous intervals, but I also want higher coverage? And in experiments, we show that partial boundary adjustment is also effective. What is partial adjustment? This is that we can set the adjustment threshold, say 0.1. It will only adjust the boundaries which has difference to its nearest stable smaller than its threshold, which means that it will adjust this one 4.925, but it won't adjust this boundary 3.2 to 3. And this experiment show the ablation results that you can see without boundary adjustment, the coverage rate is this one, but when the threshold is 0.1, the coverage rate improved, and with full adjustment, the coverage rate increased to 90%. This experiment shows that partial boundary adjustment is also effective if we want to use continuous intervals by our evaluation framework. And we also have some ordinal results because the intuition is that the intervals are adjusted to be ordinal discrete, like this. And in conformal predictions, there are some ordinal conformal predictors. They will just include those most probable consecutive rating as the interval. And here we test on 2 conformal predictors, but the results are not very ideal. Say the coverage rate are unstable and low, and the wide intervals, exist in the experiments. And then we move to an analysis part. Here we want to answer 2 questions. The first one is that why is the coverage rate below 90% in reasoning tasks? Some only 70%. And the second question is, can interval evaluation help in decision making? Because we still want to get a better score or something to represent the quality of the task or something. We still want to get a better score from interval, and we can think about this problem. The first question, why is coverage rate below 90% in reasoning tasks? Our observation is that in reasoning data sets, the calibration size is much smaller due to fewer samples. In summarization tasks, we have maybe 800 samples in calibration set, but in reasoning tasks, we only have around 200 samples in total, which means if we split the set into 50-50, the sample size of the calibration set is only 50%. It's only 100 samples. But the intuition is that in conformal prediction, if we have more samples in calibration sets, we will have more accurate quantile estimate, which would lead to more stable coverage. Then we do this ablation study with different calibration size, 25%, 50%, 75%, and 100% of the original calibration set. And for each experiment, we run with 30 times. And here you can see that insufficient calibration here leads to wide error bars. Because we run 30 times, so we can draw the error bars here. And also, sufficient calibration leads to high average. The average coverage rate are higher. than those experiments with lower calibration size. And another question is how to make decision with the interval evaluation. A simple yet effective solution is to take the midpoint of the interval. This is very intuitive, and yeah, the reasons are also simple because the midpoint is the minimum variance estimator given the interval without distribution assumption. That sometimes you know that LLMs are black box model. We don't know the distribution of the ratings, so we can just assume uniform distribution or Gaussian distribution. So without distribution assumption, midpoint is the minimum variance estimator. And it is intuitively better because it is being selected from a shorter range, say the precision interval, instead of the whole range from 1 to 5. And here is an example that we have an interval like this, and the ground truth is 3. After boundary adjustment, we have an interval from 2 to 4. And yeah, we found that in this special case, the midpoint matches the ground truth. In experiments, we show that the midpoint is a more aligned rating, especially in short intervals. In our experiment results, we found that the correlation of the midpoints to the human ground truth is higher or comparable to the row scored or weighted average of the initial judgment. Say the improvement is at most 18% in experiments though. And also the midpoints have substantially lower mean square error, substantially lower bias, and most 90% reduction in mean square error. This one you can see. And yeah, we also want to know that whether interval evaluation can help in decision making. Say, given an interval as a reference, one might make better decision in rating. Say, I give you an interval like from 1 to 3, you can say, okay, my rating is 2. Yeah. While LLMs can mimic humans to make a decision, right? So we can just test the response of LLMs when it is given an prediction interval as an inference for decision making. So the first step is that we will predict an adjusted interval by an evaluation by a LLM judge after conform prediction and boundary adjustment. And then we will prompt the adjusted interval back with previous records and ask the judge model to regrade. Here we do the experiments called reprompt and regrade by DeepSeek R1 Distill Queen 32B. And in our reprompt, we will tell the judge model its initial prompt, its initial response, and some rules about the regrade with interval. We will tell it how to make the decision chain of thought prompt with an interval as a reference. And then it will do the regrade. Say it will first measure its confidence level on initial response. And then it will predict the interval impact, which means that maybe you will think its score is outside the interval or within the interval, and then it can decide whether it should change in its grading. And in the end, it will tell you its final score. Here we have 3 observations. The first one is that when the initial rating is inside the interval, we found that reprompting seems to strengthen model confidence in initial rating. The evidence is like this, that the model's initial rating is 2, and its initial weighted average is 1.81, which measures its confidence judgment distribution. And after regrade, and its weighted score raised to 2.01 because we give an interval like from 1 to 2, and it finally give a final score of 2. Now the scores are identical, but its weighted score has increased from 1.81 to 2.01, which means that its confidence in 2 increases. And second observation is when the initial rating is outside the interval, we found that the LLM judge seems to resist to change its rating given the interval. In this example, you can see that it will first measure its confidence on its original score. You think, okay, I'm very confident of its initial response, its initial rating, but it found that the summary has some omitted details. Yeah, it fails to mention blah blah blah, which means that maybe a score of 5 is too perfect for this task. You also think that the confidence interval, this one, indicates that a higher score is possible under the uncertainty model. Yeah, which means that the judge model knows that 4 is outside this interval, but it thinks that summarization has omitted details. So it keeps its score at 4. But I think maybe it thinks 5 is too high, which means that the summarization is perfect, but we don't allow it to output 4.67, say an intermediate score in a range from 1 to 5. So let's just give it the right to output intermediate ratings. And we surprisingly found that it will just move its rating from 4 to its nearest rating within the interval. Yeah. Then we want to discuss some problems about our evaluation framework. The first one is about the sensitivity of our framework. I will introduce some discussion about problem variance, decoding temperature, and distribution shift. And we also provide an extension example in our code repository, and I will introduce some future work about this example here. Here, we want to know that interval evaluation sensitive to prompt variance. Yeah, and we found the refresh prompts yield only minor differences in the results. In this experiment, we compare two models, GPT-4o and GPT-4 mini, and we use 5 refresh COT prompts that they are very similar, or as chain of thought prompts, and we evaluate 30 times, and you can see that the interval-wise, the coverage rates are very similar. The difference is very small. Yeah. And the second one is decoding temperature, because we know the model have inherent randomness. It also has some randomness in decoding process. The temperature will influence the rating it gives. Yeah. So our problem is that interval-based evaluation sensitive to the decoding temperature, and we run an experiments about this. Here, temperature parameter is 0 or 1, and we test on 3 models, and we found that only DeepSeek R1, this model exhibits noticeable changes when the temperature changes. But yeah, other two are comparable. We also do some hypothesis testing here to test whether the coverage rate equals 90%, and we found that all p-values are very small here. Yeah, here we have a special example. In some eval dataset, there are 2 identical evaluation tasks, which means that they have the same prompt variants, same sources, same summaries, which means that the evaluation prompts, evaluation tasks are exactly the same. But though the task is exactly the same, the scores are different. One is 5 and one is 4. It might originate from inherent randomness or some other problem, but after our evaluation framework, we can do conformity prediction to get a similar continuous intervals. And after boundary adjustment, we found that these 3 intervals are exactly the same, which means that our evaluation framework can lead to more reliable evaluations. Yeah, just a special example. And for the discussion 3, it is about distribution shift. Then we want to know whether our evaluation is sensitive to the distribution shift. Yeah, here we do an experiment about this. In our paper, we have 2 datasets about summarization. One is about news summary, and another one is about dialogue summary. They are similar, but not exactly the same. Here we treat the sum eval dataset, the news summary dataset, as the calibration set, and dialogue summary dataset as the test set. as the test set, but we found only a few can achieve 90%, even with boundary adjustment. Yeah. Then we show an example to use in VLM as a judge. Say we test our evaluation framework on Gen AI bench, multimodal benchmarks. In this data set, it has some overall quality assessments of many model generated images. Say there are 1,600 prompts, and for each prompt, it has 6 model generated images. We can use VLM as a judge to evaluate the overall quality. Here we use this model and we test 2 prompts, standard prompt and channel sub prompt. Their performance are comparable. And as expected, after boundary adjustment, the coverage rate improved to above 90%. And this table shows the performance of the midpoint. Say we compare our midpoints from continuous intervals and discrete intervals to real scores and weighted average from the initial judgment. And we found that the correlation scores significantly improved, and also the bias is mitigated. Yeah. For future works, at the beginning, I mentioned that there are 3 typical types, evaluation types in LLM as a judge. Beyond the point-wise rating, we also have pairwise comparison and list-wise ranking. Yeah. And in this paper, they use the mode and mean to do pairwise comparison. We can also use the interval to do the pairwise comparison. Say this interval from 4 to 5, you can think it is much better than this interval from 1 to 2. Then we can do a pairwise comparison. Then we can extend pairwise comparison to this wise ranking, because we know the uncertainty and a more reliable evaluation for each task. Yeah. Then I will sum up today's presentation. In our paper, we introduced an evaluation framework that provides interval evaluations by conformal prediction. We will first extract logics of the target token, the rating in the model's judgment response. And then we do the offline calibration by conformal prediction and predict an interval evaluation for each task. And in experiments, we found that most intervals achieve 90% coverage rate across different settings. Yeah, we do extensive experiments to prove this. And also we found that proper calibration improves coverage rate. To obtain ordinal discrete interval that are more expandable, and we did design a technical boundary adjustment. It is very easy. Say you can treat it as just simply rounding. It will move interval boundaries to nearest variable. Then the coverage rate will increase. And we also found that midpoint is a more aligned rating because it has lower bias and maybe higher correlations to the ground truth. And we also do the report and regret experiments. That is that we can ask the judge model to regret with an interval as a reference. And we found that the judge model seems to strengthen confidence or move to nearest boundaries. And we discussed the sensitivity of our evaluation framework to prompt variance, decoding temperature, and distribution shift. We also give an example of VLM as a judge in our code repository for those people who are interested in applying our evaluation framework to get more reliable evaluation. And yeah, we also discussed the future work to move beyond to other evaluation types. So yeah, that's end of my presentation. You can raise some questions here, and I will answer it. You can also catch me in the coming Neurish conference. I will present the poster on December 7th. Yeah, thanks for listening.
Cool. Thank you very much, Huanxin, for the presentation. It's very informative. It's very nice. I guess I will use the privilege of a host. I will ask my own questions first. I personally think this is a very interesting thing because I think everybody's talking about large model as a judge has some issue, and basically you are using the conformal prediction to quantize it, to analyze the uncertainty of it. Actually, my first question is, if my understanding is correct, I think you only draw a single forward pass. So like you only run a single forward pass, you use logics, you can compute, and then use the logics, and then you use a conformal prediction to compute the interval, correct?
Yeah.
Okay, so actually my question is, I think you also mentioned you did some experiments using different temperature, right? Using different decoding temperature. Do you find the result is actually very similar? I just wonder, is there any intuition why? Because if you are changing the temperature, so the decoding logic should be very different, right? So why using this method, actually the final output is still very similar? Is there any intuition behind this?
I think the decoding temperature is an influential factors. Yeah, but maybe the inherent randomness of the model or the inherent bias of the model is more typical or critical issue. Yeah, I think the influence of a decoding temperature is limited, and we can control by the offline calibration because we can measure the variabilities of the ratings through the quantile estimate. The quantile estimate will cover 1 minus alpha % of the variabilities of or something. Then though the decoding temperature is different, maybe the quantile estimate is larger because the variability might be larger, but it actually controls the variability. So with conformal prediction, thanks to its statistical theoretical guarantee of the coverage, it can guarantee that the coverage remains 90%. Yeah, and if it fails to achieve 90%, we can use boundary adjustment.
Okay, very cool, got it. And also for the boundary adjustment, since you also mentioned this, you also mentioned like it also works well if you only do partial boundary adjustment, right?
Yeah.
So I just wonder, when should we do full boundary adjustment? When should we do partial boundary adjustment? Is there any practical guideline around this?
Yeah, this is interesting. The intuition or the motivation of boundary adjustment is that there are two reasons. The first one, we want to raise the coverage rates, and the second one is that some endpoint might have no exact meanings. Let me find maybe here. Some endpoints might have no exact meanings. Yeah, because for some tags, say you want to rate a tags, say order delivery, you can only rate 1, 2, 3, 4, 5. And non-integer score might have no exact meaning. In some scenarios, it will have this problem. Then you may need to use the full boundary adjustment. Yeah, the boundary adjustment threshold might be 0.5 here. But if you still want continuous intervals like this, say from 3.2 to 5, this one is still a continuous intervals, right? Instead of from 3 to 5, then you can use partial boundary adjustment to get higher coverage while the interval is still continuous.
Yeah, I got it. Thanks for the answer. And also, I think like in your paper, you only use a very simple boundary judgment, right? So basically, use the most nearest integer, no matter like what is the logics originally are and what's the value originally are. But I'm just thinking randomly, like maybe this part we can have some improvement if the boundary judgment can be dependent the score or the logics, right? So maybe not only directly to the closest integer.
Yeah, I fully agree. I also do some exploration in our experiment, but I haven't shown this in the paper. I think this is a more complex question because you want to get the information from the logics or the evaluation judgments, say some judgment distribution or something, to get to guide the boundary adjustment. This is a more complex thing, but rounding is effective enough, and it is very intuitive and easy. I think it is very simple yet effective. So I finally only introduced rounding here. And in our paper, we also theoretically prove that this technique has non-decreasing coverage rate, which means that after boundary adjustment, the coverage rate will increase or remain. It won't decrease. Yeah, so it means that this techniques is simple but effective and theoretically grounded. So yeah, I think rounding is a good way. Yeah.
Yeah, fully agree. I think as it's simple and effective, I think it's really good. Yeah. And also maybe I'm not pretty sure, maybe I missed something, but I think you mentioned like this method doesn't work very well on reasoning tasks.
Yeah.
But I just maybe I missed this. Like why? Like what's the exact reason behind this? Like is it just because reasoning task is more complex than visualization tasks?
I think it is not. You can think that reasoning is more complex than summarization tasks, but I think the most important reason for this phenomenon is that the calibration set size is much smaller. Since in summarization tasks we have maybe 800 samples for calibration set, but in reasoning tasks we have only 200 in total. So the calibration set is around 100. So the calibration set is much smaller. Then in conformal prediction, we know that we need more samples in calibration step to get more accurate quantile estimate. And then we can get more stable coverage. So I think this is the most important reason. And our experiments show that sufficient calibration will lead to high average, and insufficient calibration leads to wide error bars. Another reason of this phenomenon, I think, might be the rating scale. That reasoning tasks have different rating scale in our paper. That in summarization tasks, the rating scale is GPA scale, which means that an intermediate rating is allowed, say 3.33 and 4.67. This kind of ratings are allowed in the ground truth. Say we have 3 annotators in the data set. So the average score will have 13 potential ratings. But in reasoning tasks, in those data sets, there are only 1 annotator. So the potential ratings are only 5 numbers, 1, 2, 3, 4, 5. This might also influence this phenomenon, since the labels are more isolated, and it will influence the prediction result, because we use a regressor to get the interval. Since the labels are more isolated, the regression might have some problem. Yeah.
Good. So in regarding to the fewer samples you mentioned here, so it's just because like the data set you choose for the reasoning tasks is much smaller than the data set size you choose for the summarization, right?
Yeah. If you can have more annotations, more samples in calibration step or calibration process, and the results will be more reliable, say more coverage rate.
Oh, okay. And one more question is, it's maybe not about this reasoning, but I think over all the evaluation, I think you are basically considering those 4 metrics, right? Consistency, coherence, fluency, and relevance.
Yeah, for summarization tasks, we have this 4 characteristics of the
Like my question, okay, maybe this is a little bit out of the scope, but I just wonder, I assume for this table, you every time just create each metric independently, right?
Yes.
So like, right. So, but I mean, I guess maybe there will be some relation between these different metrics. So actually, I'm just randomly thinking, if we can use a conformal prediction on multi-dimensional judgment, like because currently I think we're only use the LMS judge for a single dimension, but sometimes maybe in reality we need to judge across multi-dimensions using larger models. So maybe this theory holds for single dimension, but what if we are considering multi-dimension? Right.
Yeah, sure. I think you can combine all the metrics in one evaluation run, and you can ask the model to give different score to each metric, and
Mhm.
you will face some problem, say the instruction following problem, that the model might not follow your instruction to give the same format, response format. Yeah, I mean that in some evaluation responses, you can extract the token logics very accurately, but in some other evaluation responses, you might find difficulty to extract it. You might have difficulty to target on the token logic. So if you combine all this in one evaluation, there might be have this kind of problem. As for conformal prediction, I think there are two ways. The first one is that we can extract each and do for each. We can predict intervals for each matrix if we can accurately extract the token logics for each target token. Another one is that we can combine them together, but I'm not sure whether there is some reliable method to do this. Yeah, but this is interesting and potentially can be used maybe. Yeah.
Exactly. Agree. And also, I'm also thinking maybe one extension or future direction we could do is currently, I think this evaluation method only consider on the single turn broad context evaluation, right? So basically, I'm considering if we want to use it in some multi-turn dialogue, how would let's say, the evolving context influence this? Right, but I mean, maybe this can be a future work. But I'm not pretty sure if you have any thoughts on this. Like, for instance, use the formal prediction in some multi-turn dialogue evaluation with longer history, as the history is evolving. So maybe there will be some new challenges occur.
I think maybe, yeah, there might be some changes because the longer the history, the longer the discussion to the LLM judge, yeah, it needs to extract the key information in the dialogue accurately. If it fails, it might hallucinate and tell you some non-unreliable things. Yeah, and we also test the response result, the experiments that we can ask the judge model to regrade with an interval as inference. Yeah, here the prompt is quite long because you can see that
Yeah.
in the prompt that we will include the initial prompt. In the initial prompt, we have the initial source for summarization and also the summary and also the initial response. These one are very, very long, and also the regret with interval here, this one, we give the instruction of regret with interval. This is also very long. If we, in this experiment, we actually give very long prompt to the judge model, but it seems that the judge model can still do well in the regret problem. Yeah, maybe we can further use my evaluation framework in, say, multi-agent system or multi-turn dialogues or something. Yeah, yeah, we need experiments to know whether there are other
Exactly.
changes or not. Yeah.
Yeah, fair enough. Cool. And one last question of mine is, do you think it's possible, like, we fit this interval evaluation to the pre-training stage of the larger model so that the larger model can internally estimate their uncertainty? There's
Sure.
some random thoughts.
Yeah, I fully agree because I also have this imagination. I think this might be help in, say, reinforcement learning because here we can transform a remote revolved model to an interval revolved model. Yeah, maybe an interval of a reward interval can guide a model to learn more reliably or something. Yeah, because it quantifies uncertainty, right? The reward might not be always reliable. If we can use the interval. Say we can have a lower bound and upper bound to consider in a loss function. Maybe we can have better model training.
Thanks for the answer. I guess that's all of my questions. So let me check if Leon's asking another question. Okay, one audience is asking about the open source code. Did you open source the code yet?
Sure. We
Okay.
we open our source in the GitHub repository. Yeah, and we also have an extension example I mentioned just now. This one. Yeah, for VLM as a judge. You can find a link in the abstract of our paper.
Okay. Good. Okay, so I guess from my side, I didn't see more questions online. But I think the time is also good. So thanks again, Huanxing, and thanks everybody for coming. Thanks for a nice talk. Really learned a lot to like discuss more in the future. And if you, any audience have any questions to Huanxing's work, so please also feel free to email Huanxing.
Yeah,
arrange the discussion.
You can also catch me in a numerous conference.